This is the 27th video on single agent search. And in this video, we're going to continue talking about heuristics, particularly pattern database heuristics. And here we're going to talk about how we can compress. So we're going to give some baseline techniques and ideas that are used for compressing heuristics. And in one of the next two videos, we'll be looking at how we can then use those ideas to improve using the idea of using neural networks to do compression. So this is going to get a little bit into the machine learning aspect of what and how this could be brought to bear for the types of problems we're using here. And before we get to compression, so that's the high level topic. But before we get there, we're going to do a little bit of a side onto something that are called delta heuristics. And the lectures here and some of the foundational work I mentioned in the past that Joe Culberson and Jonathan Schaefer invented the idea of a pattern database. Rich Korf made them really popular and got a lot of attention by being able to solve random Rubik's Cube instances. And then you see that Ariel Fellner, after that, did a bunch of work in looking at things like additive pattern databases and looking at a lot of techniques that you could do on top of these. And one of the techniques that he used, so he actually used compression implicitly and explicitly, but one of the compression techniques he used is called delta heuristics. We did a little bit of analysis later on. And what delta heuristics are is they're a technique that is fairly straightforward, but there's something that allow us to change the distribution of values that we have within a pattern database. And by changing the distribution, there's some nice things we can do, or we can get better properties from them. And the idea is that suppose I have some H1 and I have H2. So these are heuristics. And what I have is I want for all X that are in my state space, if I know that H1 is going to be greater than or equal to, sorry, let's put that parenthesis there, H1, sorry, yeah, well, it should be H1 of X. So H1 of X is less than or equal to H2 of X. Then what we see here is that H2 is dominating H1. H2 has strictly larger values. And so what I can do is I can make a new heuristic. We'll call this H delta to be, or H delta of X to be equal to H2 of X minus H1 of X. And so the reason we call these delta heuristics is really what we're saying, look, instead of storing a heuristic H2, which has a large set of values in it, and the heuristics are really strong there compared to H1 because they're strictly greater than them, or no more, they may be the same, but they're going to be no less. Then I can take H2 and subtract H1, and I'll just get a delta between the two heuristics. And you might ask, well, why in the world would you ever want to do this? What impact would this have in practice? And there's a number of different impacts this has, and we'll get to see some of these in the coming lectures. But let me go ahead and bring up here a picture of the distribution of states. So this is a distribution of states within a 9-tile additive pattern database. And that is the blue bars that are going across. And the values in there go all the way from 0 up to 35, 6, 7, 38. However, if we subtract from that heuristic the Manhattan distance heuristic, instead of getting values from 0 to 38, which would be 39 total values, we just get values. There's actually two things that happen. We only get even values, 0, 2, 4, 6, 8, all the way up to 20. And then instead of having 39 values inside there, we actually only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 values inside. So what we've been able to do by using a delta over Manhattan distance is we've reduced both the number of values and we've reduced the range of values that are there. So what, again, why does that matter? Why would I want to do this? Well, it ends up that Manhattan distance can be computed very easily. And now in the last video, I said that if we have a an additive heuristics, for instance, in the sliding tile puzzle, that we don't need Manhattan distance. But we could, of course, still compute Manhattan distance, and it would be, and in this case, we actually would know that any heuristic that's coming from an additive pattern database is going to be strictly greater than Manhattan distance for the tiles that are in that pattern database, because we're just going to capture those distances plus the interactions between the tiles that Manhattan distance doesn't consider. And doing that is going to give us a different distribution here. And what we see, the black tiles would be taking the delta over an 8-tile PDB. So the 8-tile PDB is about 9 times smaller than the 9-tile PDB. And so there we can get by using a smaller pattern database, and often a much smaller pattern database, Manhattan distance, as we said, we could see this as a pattern database. We can shift this distribution. And so the question we want to ask is, why is it useful to shift that distribution? And we'll provide 2 answers here in this lecture, and then, as I said, 1 answer in a future lecture. And so let's take a look, going back to our state space. And the first thing we're going to, going back to our picture here. And what we want to do is we want to start looking at a number of different compression techniques. So we're going to look at value compression, value range compression. And we're going to look at min compression. And then we'll also just look a little bit about why does compression work, or when. Okay, so let's look at value compression first. And value compression comes back to actually thinking about our previous table. So what we had is we had the 9-tile straight PDB had 39 possible values. And so it's a little bit unclear. I'll move it up to the top. And then if we looked at the 9-tile delta PDB, delta to Manhattan distance, then we reduced this to 11 values. And if we did a 9-tile delta to the 8 PDB, then we got down to 6 different values. And what we observe here is when we're storing our pattern database, we have to choose a representation to store it in. And it's easiest if we choose some number of bits in which to do that. Typically, we would say the bits would need to be some power of 2, although we can do sort of, there's other things you can do beyond that. And so if I think about the number of bits that I need, if we just think about powers of 2, then here I would need 5 bits to get to 32, so I'm going to need 6 bits to represent 39 different values. If I have 11 values, then I'm only going to need 4 bits. And if I have 6 values, I'm only going to need 3 bits. Okay, so if I take my regular, and by the way, if I were to be storing these as bytes, or trying to keep them not using, so that they would always fit compactly into a 32 or a 64-bit representation, then here we might actually be using, in a common implementation, you might actually be using 8 bits in practice. And so what we would see here is that just by using the delta PDB here, I reduce the number of values down to 11, which reduces the number of bits down to 4. And depending on how we've implemented this, we might get a 2 times reduction in the amount of memory that is actually used to store this heuristic. And I'll take a 2 times reduction, 2 times speed up or a 2 times reduction in memory any day, because there's almost no cost to doing this. Manhattan distance is extraordinarily inexpensive, and it actually can be computed incrementally, so that there's very little overhead for doing that, and then just adding that to the value that I get from the heuristic. When I pre-compute the heuristic, when I go to store it, I just remove the Manhattan distance from that state. And so that works really well. and so that, and then if I wanted to use a larger PDB, I might get further reduction here. Maybe 3 bits is something I don't care about, especially given the memory it would require to store the delta over the 8 tile pattern database. But there is another thing that we could do here. So for instance, we might notice that there are 8 values here. And what I could choose to do is, if I do the exact same thing here, so copying, but I just choose to use 8 values, then I'm going to be able to get this down to 3 bits. And what that would require is it would require maybe throwing away some of these values. And just to go back to the picture that I was showing a second ago, if we look at this pink distribution, unfortunately my mouse doesn't show up here, but if we look at this pink distribution, what we notice is that the number of states with any particular value is this distribution here, and this is a log scale. So if we look at here, how many states have a heuristic value of 20? Almost none of them have a heuristic value of 20. And in practice, what we'd be storing is we'd actually divide this by 2 and then store the value divided by 2 so that we could just store it as an integer here. But basically, there's no states that have 20, or maybe there's 1 or 2 states here that have 20. And because it's growing exponentially, actually 20, 18, and 16, there's very, very few states that have those values. So what we're able to do is say, instead of having 11 values, I could just throw off the end of my distribution. For all of those states, I can use the minimum of them. So I'll store them as 14. And the minimum of those guarantees consistency. So that's fine. And so as long as I guarantee consistency there, then I can use a 14 instead of 20, 18, and 16. And now I've been able to move down from 4 bits into 3 bits. And just because there's many, many, many things I could cover in this class, I'm not going to go into more detail about this, but there's a fairly simple optimization that you can run that decides what are the values you should remove from your heuristic in order to get down to a certain number of bits. And, so you might decide, well, I get rid of the 4s, all the 4s become 2s, and all the 20s become 18s. So there's some choices there depending on the heuristic of where you want to get rid of values and how you map them down to lower states. But basically, there's a simple optimization we can run that will allow us to determine how to map a range of values down into a smaller range of values. And in particular, what that's going to do is it's going to allow us to reduce the number of bits. So for instance, if I was using 6 bits in an efficient implementation, I can take these 11 values and get down to 3 bits, which would be a 50% compression here. And the loss that I get for the, there may be 10,000 states in the pattern database that are lost there. But if we look at the entire, pattern database, well, there's actually like 1 billion states in the state space. So losing 10,000 of them is not going to have a huge impact on, having 10,000 of them be reduced slightly is not going to have a huge impact on the number of states that I do in my search. So this is a way we can do compression here, and it's a lossy compression. It's a lossy compression when I start reducing the number of values, but it's sort of the first level of compression that we can get. And so this is the delta heuristic is enabling this because by storing the delta, I've reduced the range of values that I need. Okay, so this is just a nice technique. By storing as a delta over a default heuristic, I reduce the number of bits that I need for the pattern database. Okay, so that is value compression or value range compression. Okay, the second thing we can look at is something we call just min compression. Now, in general, we're always going to take the min when you do compression. So if I think about compressing 2 entries together, then I take the minimum of those, and that's still going to guarantee that I get an admissible heuristic. But we'll come over here and look at min compression. Okay, so that's value range compression. Let's come and look at min compression now. And we're going to make this into 2 techniques, which is div and mod. And div is basically going to say, we're going to take our pattern database. And remember, a pattern database is just a table of numbers. So what div is going to do is basically, we're going to compress k adjacent entries. And mod is going to compress a k. Well, I'll draw a picture of it in a second. It's going to compress, this is done by basically modding or divving our indices, but it's going to compress every k entries together. And the k's here are very different for what's going on for the two of these. Okay, so the idea here is that I have an original pattern database, that I have some values inside that pattern database, and what I'm going to do is I'm going to compress that pattern database by reducing adjacent entries together. Okay, and so I'm just going to make up some values here. There's no necessarily meaning to these values, but actually what we can do just for the fun of it is we'll use the array of 1, 2, 3, 4, 5, 6, 7, 8. And here we want to compress this by a factor of 2. Okay, so for div, this is going to be div. There we go, div. What we're going to do is we're going to break these up into groups of 2 entries. And what we're going to do for each of these is essentially what I'm going to do is I'm going to replace both of them by the minimum of the 2 values that are inside there. Okay, so you could just imagine going through your table and you take k adjacent entries, in this case k is 2, and you replace every entry in there with the minimum of all k values. And now what we see once we've done that process is that I can really, if I'm trying to look up a value inside here, if I look at any particular index, I can take the index, well, I actually should have numbered it starting with 0, but basically I can take the index and add 1 and divide it by 2, or subtract 1 and divide it by 2, and that's going to give me the entry into a smaller array, which is just going to have 1, 3, 5, 7. So I don't really have to store both of these values. I can just store one of them because now they're identical. And that allows me to take an array of 8 items and store 1, 3, 5, 7. When I want to use this, I compute my ranking of a state, and then I just take it, and in this case, I would just divide it by 2, and I would look up the rank divided by 2 in my array, and I would get this value 1, 3, 5, 7. And so this is going to be admissible because I might have the original value, which was an admissible heuristic, I'm taking the minimum of that. So if I was getting 2, I can't get a value that's higher 2. I might get a lower value, but I will never get a higher value here. But I've reduced the amount of memory that I have by a factor of 2. And so this is what div compression is doing, what mod compression is doing. And mod compression for this example isn't going to work as well. So if we look at here, I could just ask what is the average heuristic value. The average heuristic value here of the compressed heuristic is 16 divided by 4, is my average value is 4. If I add all of these up of my 1 to 8 and ask what the average heuristic value is, then what I have is, 36 here, I think, divided by 8. So let me just double check that. Yeah, 8 times 9 is 72, divided by 2 is 36, and then I want to divide that by my 8 entries, and so I'm going to get an average value of 4.5. So I've lost a little bit by doing the compression. I've lost on average a half, and you see this for every 2 entries, one of my entries has lost 1. 2 entries, 1 has lost 1. So when we do this with mod, what we're going to do is we're going to do something different. Is we're going to be thinking about, in this case, we're going to go mod 4. And so what I'm going to do is combine together, I'll just write this, I'm going to combine together pairs of entries that are 4 apart. So here, 1 and 5, the minimum is 1. 2 and 6, the minimum is 2. 3 and 7, the minimum is 3. So 3 and 4 and 8, the minimum is 4. And now what I end up with is as an average heuristic value. So now my actual values here would be, well, just 1, 2, 3, 4. And what I do for this is I take my ranking and I mod it by, in this case, I mod it by 4. And that will take me into these 4 entries, and I'll get, 1, 2, 3, 4. I should have been 0 indexed here, but that should be clear. Okay, so those are, or maybe I guess my numbers here, technically this is entry 0 and entry 1, 2, 3, 4. But anyway, hopefully we're able to understand at this point that those details all can be worked out fairly easily. And here what we can see is the average heuristic value here is 2.5. And so what we see is that we can use div or mod, but depending on the structure of our state space, which depends on our ranking function, and we have many different ranking functions we could use, even the order in which we rank our tiles, we may get better or worse compression. If I arrange these values in a different order, if I just did 1, 2, 3, 4, 5, 6, 7, 8, then we would get the same value as before using mod, and then the div would get the really bad value. So depending on how my state space is laid out, it may make sense to choose div or to choose mod. And one of the things we notice here is that doing this sort of compression, like if I look at my ranking function, and this is a little bit tricky to see, but if we look at our ranking functions, what's actually happening is that when I have my ranking function, the end bits or the end values in my ranking function are actually telling me something about a particular tile in the sliding tile puzzle. In Towers of Hanoi, it'd be telling where my last disk is. And so div and mod, for instance, give us the equivalent of removing the first disk from the representation or removing the last disk from the representation. And so when we're thinking about this, these operations can somewhat correspond exactly to actually just removing a disk from the representation. And so, of course, if I would do a large amount of compression, it depends, maybe removing a disk and just building the smaller pattern database, we compress the pattern database by a factor of 9, and maybe I just need to compress by a factor of 2. And so I can do that, and I just get a pattern database that is somewhere in between the large pattern database and the small pattern database. But it may be that, that actually I'd like to compress it to be even smaller. And so there is a question that comes up, which is, should I build a large pattern database and compress it? Or should I just build the smaller pattern database? Is it actually going to help me? And so again, depending on my ranking function, it may be the case that with my ranking function, when I do this div or do this mod, it becomes equivalent to just building the smaller pattern database. And there's a paper we wrote, Ariel Fellner, myself, and Malza Helmer, that looked at the theoretical details of where this happens. I'm not going to get into the full details of what is going on here, but there's a really interesting result that comes from this. And actually, there's two things that are interesting here that are going to make this be more effective in practice. So one of them is going to be a theoretical property, and the other one is actually going to be just the delta heuristic. So when I have a delta heuristic, I actually might be able to get more structure in my state space by storing a delta, because it might be that Manhattan distance actually captures some structure inside here, and then when I do this div, that I'm going to get that structure back. And so the delta heuristic can be a way in practice of actually giving me a richer heuristic, or capturing some of the values because of the correlation between the smaller heuristic and the larger heuristic. But let me show it. There's a different property here. So improving, or when does compression work? And so one is going to be if I have structure in my state space that I'm taking advantage of. And that could be just that, for instance, such as the delta. So the delta might be exploiting some structure in how this heuristic is just too higher. It may be that I have a new heuristic that on every state, almost every state, it gives me a heuristic that is exactly too higher than my original heuristic. And so when I subtract the delta, I just get a 2 everywhere, and that's like perfectly compressible. Or maybe it's perfectly compressible for 98% of my states, and therefore I just get the larger heuristic out of most of my states. So such as the delta. There has been work that shows in certain state spaces, there's some things you can do to get exact compression, like in Towers of Hanoi. I'm not going to get into that. But the second thing that's what I think is more interesting overall is that we can also get compression to work really well when the operators have dependencies. Okay. And if the high level version is this, is that if there's an operator that has a dependency associated with it, and we can compress away something to do with that operator, then we're able to actually get, our compression will have a better result than just building a smaller pattern database. Okay, and let me give 2 examples of this. Okay, so example 1 is in the sliding tile puzzle. Okay, I've been alluding to this for a couple of lectures, so here we are finally here. And the sliding tile puzzle, if we think about in our preconditions for operators, what I have as preconditions is I have adjacency. So adjacency doesn't say anything though about the items that are actually moving. And we also have preconditions that have something to do with the values in the tiles. And in particular, we know that in order to move a tile, there must be a blank sitting somewhere in the world. But there's no conditions like about the 1, or about the 5, or about any other number, which I didn't write here. The only condition is on the blank. And it can be shown, or it has been shown, that if I have that, because there is a condition on the operator of the blank, then if I do something that is equivalent to compressing away the blank, I'm going to be able to keep those dependencies in the values of my pattern database, and I'll get larger values than I would otherwise. So what that says is compressing away the 1 or compressing away the 5 is just going to be equivalent to building a smaller pattern database. But if I compress away the blank, then I'm actually capturing, there'll be some information which is captured in the pattern database, which still gives us the distances that have something to do with the blank being there. So this is why in the sliding tile puzzle, we almost always compress away the blank. Now, this may not make exact sense why this is the case, but in the second case in Towers of Hanoi, this will become completely obvious. And remember in Towers of Hanoi, I mentioned this, that what we're going to do when we build a compression or when I build a pattern database, that there's 2 things that are going on. So compression, when I think about my state representation, so if I have 4 disks here, I can have, this could be disk 1, so these are my disks, 2, 3, 4, and then inside there would be the locations. What happens here is that div is, if I div by, since there's, actually I want the 4 peg here, sorry. So if I do a div operation, when I divide, it's equivalent to getting rid of the bottom bits here. And so this is equivalent to saying like, just get rid of disk 4. And when I get rid of disk 4, so if I think about getting rid of disk 4, it doesn't really change the solution for disk 1, 2, and 3. I can get my complete solution for disk 1, 2, and 3, and I could be using that as a heuristic for maybe even the 10 disk Towers of Hanoi. But getting rid of the 4th one here doesn't, like my distances are not going to be impacted in it. It will be exactly the same as building one with the top 3. But in this case, if I were to use mod, and now if I were just to be representing disk 1 at the bottom, if this was disk 1 and that was disk 4, then what I'm saying about div and mod would be reversed. But if you think about mod, what it's talking about, what mod is saying actually, and I'm going to highlight this, is that mod is getting rid of the top disk here. And if we ask in Towers of Hanoi, what are the dependencies of an operator? The dependencies of the operator are that to move a particular disk, there cannot be another disk on top, which has well, there just can't be one on top in order to move that disk. And so if there is, then I'm not allowed to move that. And so what that says is that if I do compression and I remove with my compression the disks that are at the bottom, then it has no impact because there's no dependencies on my operators on the disks on the bottom. But if I do compression and I remove in my compression the disks on the top, I'm going to be preserving in my database something about these dependencies. And I'm going to get much larger heuristic values than when I compress the bottom. Is essentially, it's just the same as building a smaller pattern database. Okay, and so if you think about this for the sliding tile puzzle, or sorry, for the Towers of Hanoi, what's happening here is, hey, I've got this disk here, and when I do the actual computation in this state space of the optimal solution to get to the goal, or the solution, it's really the solution distance from the goal. As part of that solution, I'm going to be moving this top disk all over the place, and then I'm finally going to put it in at the end. And if I compress away this top disk right here, when I get my distances for moving these 3 disks, they're still going to incorporate the fact that we had to move this top disk out of the way in order to move these disks down at the bottom. And because we've captured that distance, what happens is we're going to get much larger distances for these bottom disks than we would get if we only looked at the disks on top. Okay, so we essentially, by compressing away the top disk here, which is the one that has the dependency, we still have this disk's interactions with the other ones as part of the pattern database. They're still captured in the compressed values, although they weren't previously. Or sorry, they wouldn't be if I did it the other way around. And by capturing that, I get much higher heuristic values than doing it the other way. Okay, so if this explanation doesn't give you a good intuition for what is going on, this might just be something that you'd have to run and implement and look at the values and see what you get. But if you do that, what you will see is that that you get much higher values doing one of these, either mod or div, depending on the ordering in which you've ordered your states. And the reasoning for this is the dependencies. If I can compress away the dependencies, then I'm going to get better heuristic values than I would get for not compressing away dependencies. Now, these are the 3 things that I said I would cover today. So this value compression, or in this video, the min compression and why does it work. I do just want to mention really briefly that there are quite a range of other compression techniques that have been used. And so I'll mention 1 or 2 of these other techniques. And so let's look, I'm going to just show you here the distribution of the Rubik's Cube. And if we look at the distribution of the Rubik's Cube, what we actually see is that the heuristic values, so this is the 12-edge Rubik's Cube. And so this pattern database would take, if we store it, we build it using external memory. It requires about, there's 980 billion states inside here. And so that's taking, when we store it with 4 bits per state, it's going to take about 500 gigabytes of memory. And most machines that people have these days don't have 500 gigabytes of memory. So we can't fit this into memory. Oh, and this is something I meant to say earlier. Why do we compress? Obviously, we just compress so that I can fit more things in memory, but oftentimes we have pattern databases that are bigger than memory. And I'd like to be able to use them in memory of maybe a smaller device or something like that. And so what we notice here is actually that most of the depth is, so most of the values are 10, 11, and 12. Basically, if you look there, that's 8, 9, that's 9.5 out of like 9.8, 980 billion states. And there's very few states that are anywhere else in the state space except 10 or 11 or 12. When I'm actually running IDA star, and we're going to see some of this in, again, in an upcoming lecture, it ends up that the low values are very important for something like IDA star in a search. And so, actually, I don't know if I'm going to talk about it too much, but low values are actually really important. And so what we find is actually, we don't necessarily have to store the 10, 11, and 12. And so I could, if I just store all the depths from 0 to 9 and say everything else is 10, we capture most of the distances. So this is a little bit like value range compression, but we can use other techniques to, instead of storing every state, we could actually just store like in a hash table or in some sort of optimized hash table, depth 0 to 9. I'm only storing about 10% of the entire state space, and I might be able to do this much more efficiently. And there's a number of techniques like Bloom filters and things like that that can be used for doing this efficiently. So we can look at some problems and we can find problem-specific details about what our distribution of states are, and we can take advantage of that distribution to be able to get a heuristic that is still admissible but captures most of the information in a much smaller way. Okay, so there are, as I said, there's a bunch of techniques like that. I'm not going to mention all of them. There are also techniques like using the dual, which I mentioned when we were talking about ranking, that allows me to do multiple lookups in a single pattern database. And so when I have, a single pattern database and I can get multiple lookups out of it, then that can be just as good as having multiple pattern databases and just doing one lookup per pattern database. Similarly, many state spaces have a symmetry to them. So in the sliding tile puzzle, you can actually flip along a diagonal axis, depending on where the blank is in the goal, but you can flip around a diagonal axis. I can just write this here, or I'll just show what that axis is. It's this one. So I can basically flip these states. I get a different state. I have to do some other conversions to be able to do this. But when I flip along this axis, I get another lookup that I can do from a symmetric lookup there. And that would allow me, again, to get multiple lookups out of a single pattern database. And as I said, so there's a whole range of techniques like this we can use that allow us to start to exploit the data inside a pattern database so that we can get multiple lookups, and therefore I need fewer pattern databases, or I can compress them down into, especially when there are dependencies in the state space, I can compress down things related to those dependencies, and that will allow me to capture most of the heuristic value in a much smaller pattern database. And there's also other things. I'll just mention it here since this is sort of the grab bag at the end here. It's also the case that sometimes we could build many small pattern databases instead of one large one. And at least for unidirectional search, that works really well. So unidirectional search really needs low heuristic values to work well. Bidirectional search actually doesn't need low values, it needs high values. So the technique that you want to use here may depend on whether you're wanting to use unidirectional search or bidirectional search. Just to say, like, I'm going to end this here, but there's just a lot that can be done for compression by taking advantage of these. And so in the next video, I'm going to talk about how we can use neural networks for doing compression. And that's going to just give us an example of then how we can put together this set of the knowledge that we have here and understanding and put it together into something now using machine learning to get admissible heuristics out of it. So we'll continue that in the next video.